So, I'm going to talk about a case study, and this is a study that's literally been going on in the lab for about 8 years now. We started a study to try and understand how things change and how people respond to different diets and how quickly they respond. And so, using some targeted metabolomics. All right, so as you know, this molecular phenotyping, obesity, and nutrition, this is a lot of what we do, and we're trying to figure out, if you eat this, what happens down here, and can you actually understand how this relates to the phenotypic output of individuals. And so, nutrients, as you know, are really important for everything we do, and they're the most inescapable environmental perturbation that we do in our system. The exposure, the amount of the exposure compared to your genetic predisposition and your genetic control, your metabolite levels, obviously these two things are going to interact to give you what your final metabolome is. Measure of diet intake, as anybody in this room knows, especially my friend Karen, she's not here, who's the head of human nutrition, is wrought with errors. It's really hard to get an accurate idea of how much people eat and what their macronutrient mix is. It's estimated that half of the Framingham data that has been collected on nutrition, half of it's biologically impossible from either the amount or the amount people are eating or the macronutrient mix that they claim. There have been a number of studies trying to define the relationship between macro and micronutrient intake and specific metabolite levels. Folate and birth defects and protein hypertension, there's relationships between these things, and we know we can measure these things and predict outcomes. But objective assessment is there. So we started studying. We've actually since done some more studies, but I'm going to just show you this first study that we did is we took people and fed them an isocaloric diet, either a high polyunsaturated fatty acid diet during period 1, and then we switched them immediately to a high carbohydrate diet, an isocaloric diet, keeping the protein pretty much constant and changing the carbohydrate to fat ratio, and then looking at what their metabolome looked like. And so we provided all the food that people ate for these this actually 42-day period. The people in the M crew were very good about adjusting the dietary intake to keep the people's weight stable throughout the whole thing. So they would adjust the caloric intake, and we had less than 1% variation in weight across the study. So, and that's what's shown here. So, so these individuals, they've been very stable across the time. And you can see there's a range of weights. That's a mix of about 50-50 males and females in the study. So we're going to see, so what is the difference between phenotypic responses? And this is actually, sort of didn't surprise me, but then it surprised me, when you keep looking at it. So if you look at the triglyceride response, this is what the people's triglycerides were at baseline, and then you give a high polyunsaturated fat diet, the triglyceride levels went down markedly, and some of the people were higher, and then when you gave them a carbohydrate diet, they went back up. If you look at the HDL, there's similar sort of patterns, but not everybody responds to these diets in the same way, and so is there a way of actually predicting how people are going to respond to a diet from at least some of these cardiovascular risk markers? The interesting thing is just about everybody's LDL cholesterol went down after 21 days without changing weight on a polyunsaturated fat diet versus the carbohydrate diet. Now, some of this has been seen before. We also did glucose tolerance tests on people just to see how they responded. And what you can see from this figure here is that there's a variety of responses. So some people at baseline versus 120 minutes, this person, their 120-minute glucose was markedly lower. Some of these people went down a little bit, some went up. You put people, these same people, 21 days of polyunsaturated fat diet, you can see that there's a similar change in response. This light green person here now is going down, but most of the people actually have a higher 120-minute time point. And then when you put them on a carbohydrate diet, then you get back to this, sort of a mixed response. Some people go up, some people go down, and they don't change in a predictable manner going from one state to the other. So there is obviously a mixed phenotypic response to different diets, even for a short-term intervention. And this just shows, this person went down, this person went down on baseline diet, on a polyunsaturated fat diet, and this went up, and this person went up, and this person went down. And so there's something different about people. Now, glucose tolerance tests are actually very reproducible among people. If you do it one day to another, they tend to have a stereotypic response if you don't change their diet. We also looked at a small subgroup of people. This actually came out of a study we started with people with hepatitis C to see if we could actually change their viral load. We also took some people with non-alcoholic fatty liver disease. These people are much more stereotypic in their response. They go up, a polyunsaturated fat diet, they're still going up. And so they always have a high 2-hour blood glucose compared to their baseline. And then if we looked at the response of their AST, a measure of their liver function, you can see that there's a differential response between these individuals. Very small numbers, but it just shows you the variability that you can have in some of these things. So we did targeted metabolomic profiling. And the thing I actually wanted to show more than anything in this is the next couple of slides. So here's what we did is we looked at the correlation between the levels of different metabolites in these individuals. And so these are some of the demographic characterizations, their age, their BMI, and things like that. But then across the top and the bottom is isocarotene, these intermediates of fatty acid metabolism, amino acids, the phospholipids, the isoglyceroids, free fatty acids, and within these lipids, there's different chain lengths of fatty acids, or these are the total fatty acids within each of these things. And you can see between the control and the people with non-alcoholic fatty liver disease at their baseline that there is areas of high correlation between some of the lipids, which is probably not surprising to anybody. There's inverse correlation with some of the lipids and some of the isocarotenes that we see. And so there's these different patterns. And one of the things you can see in the people with non-alcoholic fatty liver disease, and we actually have some more individuals with this now, is that you see the pattern is a little bit different. There's some consistencies, but in certain areas there actually is, over here there's positive correlations, there's negative correlations over here. You can see it's a much more checkered thing on the right side. So this is at baseline. Here's what happens on the PUFA diet to these correlations. So if you flip back and forth, the people, the controls tend to stay pretty much the same. The people with non-alcoholic fatty liver disease change a little bit differently. We were really surprised when we ran the next one, what happens on this is the carbohydrate diet. It's mislabeled, I apologize. So this is after feeding 21 days of carbohydrates. What you can see is that compared to the PUFA diet, there's a marked increase in the correlations in people in the controls between a lot of these different positive and negative correlations between these different metabolites. And then the amazing thing was how sort of monotonic people got on a high carbohydrate diet who had non-alcoholic fatty liver disease. It's sort of like everything now started to become very much the same and correlated up and down. So we've been thinking about this, and this is the first time I've shown this. I've shown this to people in the lab, and they laugh at me. So we'll see if you actually. One more slide before I do that. This is what happens if you actually take obese individuals and look at their correlations. It's plotted a little bit differently, but you can see obese individuals, you have this nice, dark, highly correlated area in the middle here, and then some negative correlations between some of these amino acids and some of these lipids. When you take these exact individuals and you go put them in a weight loss program over about 4 months, and this is about 22 people, I believe, and 22.5% weight loss, you can see that this very monotonic area here now becomes stippled. And what this is actually a alternation between a saturated and a monounsaturated fatty acid, saturated, monounsaturated. So you start actually changing the patterns and the relationships between different lipids, where here you have a high correlation between a lot of these lipids. Here now you start getting negative correlations. And so by reducing the amount of food that's coming into the system, you start cleaning up the metabolism. You can actually start seeing differences. And so we think this may be a way of looking at how much people are overeating and what they're eating as well. All right. So here's the thing. Maureen and Al are going to laugh, but so this is how I try and think about these correlations. because it's going to come back to this whole thing about since metabolites are not truly independent of each other. So this is sheep through a bottleneck, which is the fence that they're trying to go through. And so if you think of this as a bunch of metabolites coming into a system, let's say they're fatty acids, they're getting metabolized. And right now, everybody's competing against each other, and so everything's backing up. And if you change the colors a little bit, what you can see is, let's say these are polyunsaturated fatty acids, these are saturated fatty acids, so you have different flows coming in, and depending upon how big you are or how well you interact with enzymes and things like that, you're going to get through this gate at different rates, and so you're interconverting one thing to another. But everybody's backing up, and so if everybody's backing up here, you're going to have a high correlation between a lot of these metabolites. And so where you see, when you actually challenge the system, where you see a lot more correlations, it really does tell you where there's actually bottlenecks in metabolic fluxes through different pathways. Now, I tried to color these because these are precursor-product relationships, and sometimes these are highly correlated. If there's another bottleneck up in here, then these correlations break up. And you can actually start seeing patterns if you look through the metabolic pathway about how things are highly correlated and not highly correlated, and can give you some insight into how much is coming into into a bottleneck in metabolism. So if you actually lose a lot of weight, what you're going to see is that there's a lot less stuff coming in. You're going to change the metabolites that are coming in, and you'll actually be able to change your flow and how much is actually going through. And so these differences, if you can actually start mapping these and quantifying these kinds of things, you should be able to find where you have changes in the utilization of different metabolites and different metabolic pathways. And so it's something that we've been working on, trying to understand these, how you can actually use this to map out different things. As I said before, we've been looking at some samples from Northeast Africa where these people don't overeat, and their metabolism is like this, and then, oops, our Westerners are much more like this. We have a really high correlation between different metabolites. It goes down a whole lot when you actually look at samples from people who have lost weight or generally are not overweight. I'm going to skip this because Alice said I have to go faster. So here's a very simple plot of some of the lipids that we saw. So remember I said that we took free fatty acids, we looked at the triacylglycerols, and what we did is we looked at the chain lengths and the double bonds that are across here. And you can see, I think, that the triacylglycerols, the fatty acid triacylglycerols, their pattern changes after, so this is a baseline after 2, 7, and 21 days of the polyunsaturated fat diet. You can see these lipids go down, whereas these other lipids are going up, and then you change into a carbohydrate diet. These shorter chain saturated fatty acids are going up. And so you can actually see a dynamic pattern in the triacylglycerol. And so they change much more quickly than the diacylglycerols or the cholesterol esters, these different kinds of lipids. And so down here I've plotted where in this time course there's actually a statistically significant difference. And so what you can see is that the lipids in the triacylglycerols and to a lesser extent the cholesterol esters change much more quickly than the lipids in these other fractions, the diacylglycerols or the phospholipids, suggesting that you might be able to use some of these the lipid levels to see what short-term and longer-term intake is. So there's some things that change very quickly and some things that change much more slowly. And if we actually do principal component analysis and look at the percent lipids, you can in these at the 18.2 and 14.0 predict PUFA days 2, 7, and 21, and monounsaturated fatty acids, shorter chain monounsaturated fatty acids, which are being generated de novo because of a high carbohydrate diet. You get de novo lipogenesis, increase the steroid desaturase enzyme, and so these actually are predictive of having a higher carbohydrate intake. I'll skip over this. It's an interesting thing. And then working with a little bit more complex, we took these same samples And we did a lipidomic assay on it, the TM, and we'll talk about this a little bit later. So we looked at, I forget exactly how many lipids are here, so 400 some lipids. And so this is at baseline, and then we can actually look at the dynamic change in a number of different lipids. And the thing to point out is that you see a lot of lipids change quickly, some of them change more slowly, and none, and a subset also don't change across this 21 days with changes in diet. So here's the, again, the polyunsaturated fat diet. You get a rapid change at 2 days and then no change at 7 or 21 days. And this is the total change right here. So this is a change in the first 2 days. There's a little bit of readjustment in the triglyceride fraction. And then at the end, what you can see is that there's no more change at 21 from 7 days, and here's the total change. And so a lot of these things are changing very quickly. So this gets back to this whole thing about what you want to do when you're trying to look at different interventions and how the diet can actually very rapidly change. So it really can make a difference what people eat just a couple days before you do an intervention. And to try and reduce these variabilities when you're trying to do metabolomics, if you can within experiments, is trying to get people to eat a similar diet across time. And so we've now continued these experiments. We have another set coming out, and we'll see how fast we can actually change these things. Now this goes back to, and this is again one of George's students. It's one of my favorite plots. This is the correlation of all these 400 some lipids that we had, and this is the correlation between them under the polyunsaturated fat diet after 21 days, and then after the carbohydrate diet. And again, what you can see is that there's much more connection between different lipids under a higher carbohydrate diet than a polyunsaturated fat diet. And so again, can you use this information about these correlations and about these patterns to help you understand what people are eating in a much more unambiguous fashion? This is just what Thiel did also is you can see how here these are connected to here, so there's actually positive correlations between these lipids down here and these lipids up here, and there's some negative correlation. You can make these sub-networks, and you can see that you can now consolidate all these different things into these sub-networks, and these probably have information in them and how these sub-networks are formed, and perhaps the connectivity between these sub-networks may be able to be quantified to be able to get an idea of how much people are eating. So if you think about it, if you actually add somebody in here who's eating a diet that's unknown, does it disrupt the connectivity between all these things, and can that be quantified? So these are some of the things that we're working on. I'm going to skip this. And then if we, can you use something like a PCA plot? This is something that I drew on a napkin. I'm showing this just because George is here, because he actually reminded me of it last night, that we trying to understand, can you use where people are in PCA plots? And so this is the original data from these individuals under different dietary conditions in different days. What you can see is that, it's hard to see from here, but you can see that when we have people that are eating the polyunsaturated, the fat diet, these are cyan at 2, 7, and 21 days. They all move over in this area here. People on the carbohydrate diet are over here. And what you see is that there are some people who cluster up in here where that they're clustering with carbohydrate eaters. These people are fat eaters. These probably are intermediates, and then we don't know what that person is doing. One of the drawbacks of this experiment is that we didn't actually do a dietary assessment at baseline. So we've done, with Karen's help, we've now done, we redid this experiment trying to define what their diet is before we go there. So I just wanted to show you, again, this is I harp on these things because I do nutrition sort of related stuff, and that knowing what people are eating at baseline or trying to control is really going to be an important thing to get really nice metabolomes if you're doing human studies. Or when you look at your metabolomic profiles and you have different groups, don't be fooled that some of the differences that you may be seeing if you're going to do metabolomic assays may be due to their dietary intake versus other things that you're looking at. And so I'll stop there. If anybody has any quick questions, I'll be happy to answer them. I'm sorry? We have time. Okay. One quick. All right. So thanks. What are we going to do now, Ala? Oh, Karen.
I guess I do have a question, which I probably should know the answer to. So the subnetworks are defined statistically by George and his wizardry, or how do they relate to sort of known subclasses of lipids?
One of the questions that we have, I'm going to answer it a different way, and I'll come back to how do they relate to the subclasses. So if you go back to how these things actually are correlating, these subclasses, you can see that that lipids that are somewhat related. So the phosphatidylcholines, if I can show you those, they're up on the top here. Or let's just do the diacylglycerides are up here. They have a high correlation with the triglycerides. And that's not surprising. When you actually do triglyceride, de novo triglyceride synthesis, some of the diglycerides that are there actually will escape out into the blood. So there seems to be a high correlation between those. Although they seem to be turn over very rapidly. When I showed you earlier with just looking at the lipids, that diglyceride fraction was not a very good predictor of dietary intake, at least the fatty acids. Probably because it's very transient, and it's actually really the triglycerides which have the information in it. So there's those kind of relationships we know about. Because there is correlations between some of the phosphatidylcholines and the PCs here and the triglycerides. They're clustering down in here in this subnetwork. It's probably a similar thing. As you're doing de novo lipogenesis, you're putting different lipids in, or when you're taking them in the diet, you're putting in different classes, and they're filling up in a similar manner. And so some of it is actually because of the chain lengths and things like that. Okay, thanks.
Now, let's have a break for 10, 15 minutes, 10 minutes.
Okay.
And then we'll continue.
Okay. Hi.